Hi everyone, just had a few questions about finding the general term. And so I'm just going to show you a few different examples. I'm going to start with some easy ones and then I'm going to go through your textbook questions, or some of your textbook questions, as well as to how to find the general term. So then what they mean by the general term is if I was to input any place value, what would the number be at that place value? So you're looking for the value at the nth position, and whatever you decide what the nth position is. Now this first arithmetic sequence, we know it's arithmetic because every single time we're adding 3. So to get from 5 to 8, you add 3. To get from 8 to 11, you add 3. To get from 11 to 14, you add 3, and etc, etc, etc. So we know somewhere in our general term formula we're going to have a 3. So we're going to have it's like a 3 times n there. But if we look at this, if we just said 3 times n is our solution, and I went, okay, well, place value 1, 3 times 1 is 3, not 5. So we need to add 2 on to get to 5, and then we just need to make sure that that would work, because then for place value 2, does it still work? 3 times 2 is 6, and then we add 2 to get to 8. Oh, yep, that works. 3 times 3 is 9, we add 2 to get to 11. So then our, I've left way too big a gap there, I do apologise. Our actual formula is just going to be 3n plus 2, hopefully without your massive gap just there. So that would be the general term for that formula, and it's an arithmetic sequence. For a geometric sequence, there's not the same difference. So the difference between 2 and 4 is only 2. The difference between 4 and 8 is now 4. And now it's 8, and now it's 16. So the difference is changing, but what you might notice is that we are multiplying by the same amount each time. So to get from 2 to 4, we're timesing by 2. From 4 to 8, we're timesing by 2. From 8 to 16, we're timesing by 2, etc. So we know, because it's a geometric sequence, our general term is not going to be 2 times something, even though we're timesing by 2. We had a plus up here and we ended up with 3 times n. So here we're actually going to raise it to the power. So it's going to be 2 to the power of n. And then we'll check that it works. In place value 1, so this is place value 1, place value 2, 3, 4, etc. In place value 1, 2 to the power of 1 is 2, yep. In place value 2, 2 to the power of place value 2, 2 squared is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16. So this is our general solution for this term. Now I'm just going to show you that if this term didn't start at 2, we're lucky that it started at 2. If, however, it was something like, let's say we started from 8. So if it went 8, 16, 32, 64, we can't use just 2 to the power of n, because that would have us starting at 2. We actually want to make it start at, this is now our 1, so 2 to the power of what is 8? Well, we know that 2 to the power of 3 is 8. So we need to go from n to n plus 2 here. So we've gone up 2. So now, in place value, because if this is, I'm crossing off this one, so pretending this is a new sequence. If this is our place value 1, this is our place value 2, this is our place value 3. So now in place value 1, instead of 2 to the power of 1, I've got 2 to the power of 1 plus 2, which is cubed. So that would be 2 cubed, which is 8. And then we'd move on to this one. Instead of just the 2 squared for 2, we'd have 2 plus 2, which is 4. 2 to the power of 4 is 16. So see how it changes depending on where you start. This is a similar geometric sequence in that we're still doing 2 to the power of something, but we've started at a different point. So our general term equation has to change. Let's have a look at some examples from the textbook. So this one here, the first one that you're asked to start with is this one where we're going from 10 to 50. Now if I just had those two terms, I'd be like, oh, we're timesing by 5. But then we go to 250, and then we go to 1250. So we're still timesing by 5 with each one. So we don't have a common difference. We're not adding 40 each time. We're timesing by 5, timesing by 5, timesing by 5. Which means that it's going to be 5 to the power of something. So it's going to be 5 to the power of n, and we're going to need something here. So, but let's look at where we're starting from as well, because we're not starting at 5 to the power. If this was just 5 to the power of 1, so this is our place value, 1, 2, 3, this is our third term, fourth term, etc. So at our first term, 5 to the power of 1 would be 5, but we've got 10. So that's not going to work. We can't really change 5 into 10 from a place value, but we can change 5 into 1. So we're going to go minus 1 here, and that would be 5 to the power of 0. So that would get us 1, because anything to the power of 0 is 1, and then we can multiply by 10. Sorry, that was my phone. I should be on silent. So now we've got 10 times 5 to the negative 1, the power of n minus 1 up here, which means that we're going back one place value there. And this is actually, we just need to make sure that this works with our actual, all of our other terms. So in our second place value, we'll start with this bit because order of operations. 5 to the power of 2 minus 1 would be 1. So 5 to the power of 1 is 5. 10 times 5 is 50. So that works. Third place value, n minus 1 would be 2. 5 squared is 25. 10 times 25 is 250. So our general term works here. Next one down, oh, and this is a geometric because we've got a common ratio, which means we're multiplying by the same thing each time. I'm just going to put geo. Number B. Notice that we're not multiplying each time, we're subtracting each time. So we're going from negative 1, and we're going negative 6. Oh my goodness, my brain. We're going negative 6 on this one. Negative 6, negative 6, and then if we kept going, it would be negative 6 again. So we know we're going to have, for our general term, it's going to be negative 6 times some version of n in there. But if this was my first term, if this was my general equation, then my first term should be minus 6 times 1. So we should have started at minus 6. But we've started at 41, which means we just need to work out what the difference is from minus 6 to 41. And what's the difference there? And that difference is 47. So our first term is going to be minus 6 times 1, because remember that's our first term, second term, third term, fourth term, etc. So minus 6 times 1 plus 47, that would get us to 41. Minus 6 times 2, so minus 12, plus 47 would get us to 35, etc., etc., etc. So that becomes that one, and that is an arithmetic sequence. This next one here looks a little bit more complicated. So let's notice what's happening here. Two things. We're alternating. This is actually called an alternating series. We're alternating between a positive, so I'm just going to slip in some positives there. Positives, negative, positive, negative. And there's only one way we can really make that happen, is we can have a negative 1 to the power of n, but not just n, we want it to keep changing. So if negative 1 to the power of n, or that would change, negative 1 to the power of n is going to change because negative 1 squared would be a positive, negative 1 cubed would be negative, negative 1 to the power of 4 would be positive. So that's going to make us alternate. So we're going to start with that there. And then notice down the bottom, we're multiplying by 3 down the bottom. Multiplying by 3. Now I'm saying multiplying by 3 down the bottom because we're ending up with a fraction here, I'm going to assume that our general term is going to be an equation. You could say that you're dividing by 3 in the whole thing, but we're multiplying by 3 at the denominator still works in the way I think of it. So just at the denominator level, which means that we're going to have some type of 3 to the power of n down the bottom here. But this is kind of a bit funny here because if I try and put my first one in here, 3 to the power of 1 is still going to be 3 minus 1 to the power of n, so that would be minus 1 to the power of 1, so we'd have minus a third here. And I don't want to start with minus a third, I want to start with a positive third, which means that I need to change, we're not starting with the actual term number up here, I'm going to go plus 1. Now, interestingly, you could go minus 1 here, you just need to make sure that this thing up here is 1 out. Now let's try it. If my first place value, my first term number 1, I'd have 1 plus 1, so now we're squaring it up, that's going to make our minus 1 positive. Divided by 3 to the power of 1, so 3. And that would get us positive a third. Let's try it with our place value 2 just to make sure that this is the right answer. So trying it with place value 2, we would have negative 1 to the 2 plus 1, so we're now cubing, divided by 3 squared, which would equal negative 1 cubed. All you need to realise with that, it's still going to be a 1, but is it going to be positive or negative? Well, cubing is a odd number, which means we're going to stay as a negative, and over the top of 3 squared, which is 9, oh, that's working. And it would work with the next ones as well. Lastly, oh, by the way, that is a geometric sequence, not a series. That's a geometric sequence because we're multiplying by 3 each time. This one here, you might recognize that this is a Fibonacci sequence, which means it's neither geometric or arithmetic. You might have noticed yesterday it's actually called a recursive sequence because each new term relies on the terms beforehand. And you might even, like if you recognized it, you might have recognized it from the slides that our general term formula is going to be what we're about to discover. So you might already just look at this and be like, oh, we've already been given the answer here. But let's pretend that we haven't been given the answer. So notice here that we're adding the first two. So 1 plus 0 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5. You know how the Fibonacci sequence works. So that's just what we have to express. So our u to the n, our general formula, is going to be the first term, and I could even put for term number 1 here, but then I'm just specifically saying that this term equals it. So I still want to be a little bit general. So I'm going to say it's going to be n minus 1 plus u to the n minus 2. And you could write it slightly differently if you wanted. Like you could have these the other way around. That would be fine as well. But all I'm saying is here, if I want to find one term, I have to find the term before it and then the term before that, so n minus 2, and add them together. And that's all you would be doing. So that means that if I wanted to find, let's say this one, if this is 1, 2, 4, oh, that's 3, 5, if I wanted to find the 5th term, I would have to find the 5 minus 1 is 4th term, and I would have to find 5 minus 2 term, which would be the 3, and I have to add them together, and then I get 5. And that works. That's how you do it. Have a go at the next ones in that exercise. They can be a little bit tricky, so email me if you are having trouble. But basically, you just need to look at what you have to do, get a basic thing down, and then work out what you have to change or alter. So if you have to, like for this one, we had to start with n minus 1 as our power, because otherwise we'd have 10 times 5 to the power of 1. So we'd have 50 to start with, and we didn't want to start with 50, we wanted to start with 10, so we had to have a 0 here, and so we needed n minus 1, that kind of thing. So it just takes, start with your basic thing, you know it's going to be 5 to the power of something, and then work out whether you need to add 1 depending on where you're starting, or subtract 1 depending on where you're starting, and whether you need a number here as well, because otherwise it would be 525, and we didn't want that either. Let me know how you go.